Let's take a look at a regression model in Azure ML. So here I am in my Azure ML Learning Studio, and I've got my calories experiment that we started previously, and you can see I've got the calories and the exercise files. I've joined them just as we did before, and then I converted them to a CSV so I could do some visualization of them and see some of the relationships. Now I've added a few more modules to this, and I'll just walk you through what we've done very quickly here. We have got an edit metadata module here, and what I'm doing there is I'm taking that gender column. If you remember, there's a gender column. Just visualize this, which is male or female, and that's obviously not a numeric value, it's a category, it's a categorical variable. So I'm making it categorical. If I have a look at the properties in here, you can see that I am just saying this is categorical, so treat it as a categorical variable. Then I've got an apply math operation here, and what I'm doing here is I'm taking duration and heart rate, and if you remember when we compared some of these different values to calories, when we looked at the scatter plot, there were kind of curved relationships that weren't exactly linear. So sometimes just having another version, doing what we call feature engineering, creating another feature based off an existing feature with a different kind of mathematical calculation can help me build up a better relationship. So going for a power of 2, basically squaring these columns, gives me an alternative way to compare them, and by squaring them I might find I get a better fit against calories. So then there's another math operation here to calories itself. I'm actually changing my calories label that I want to predict, and I'm changing it to the log of calories. I'm using a natural log function. Now there is a reason I'm doing that. I'm not just being contrary. I want to make sure that I don't predict any negative calories, because of course you can't burn negative calories. So we're converting that to log so that our prediction will actually be log of calories rather than calories, and it will always be a positive number. Now then, it's really common to normalize or scale the data that we're working with. If we've got lots of different numeric values all on different scales, that can mean that values that have a particularly high number can dominate the training of the model when we come to create our regression model. So we're scaling them all to be a value between 0 and 1 effectively. And I'm using a couple of different types of normalization. The numerics that have a reasonably normal distribution, in other words, the ones that have that kind of bell-shaped curved histogram, I'm using something called z-score normalization to bring those down into the same scale. And in the ones that aren't kind of normal distributions, there's a couple of columns in there, like the age and the duration and the duration squared. They aren't really sort of normal looking distributions, so I'm going to use this min-max version of normalization. It just works better for that type of distribution. Then I've got a little bit of tidy up work here. User ID and calories. Well, user ID is not really a very useful predictive column. It's just a unique ID for each user, so it shouldn't have any bearing on how many calories they burn. And calories itself is the original label that I'm trying to predict, although now I'm trying to predict the log of calories. So I don't want to use calories as a feature. So I'm basically just saying these aren't features, don't consider them when we're building the model. All right, well then we get into the actual model building, and the first thing I'm going to do is split the data randomly into 2 sets, and that's because this is an example of supervised learning. So I'm going to take 70% of my data and use that to train a model, but I'm going to hold back 30% of that training so that I can then test the model using some observations where I actually know what the label should be, and that lets me see how accurately the model is predicting. So we've got that 70-30 split there. And then we train the model, and we're training a model using a linear regression algorithm. There's lots of different algorithms you can use for training regression models. In fact, for all different types of models, we're going to use linear regression, which is a fairly traditional, kind of well-known algorithm for training these types of models. We're training the model to predict the log of calories, that ln calories that we calculated earlier on. And then once we've trained it, we are going to score it by comparing the predictions that get generated with the data from our our test set that we held back. So we'll score it, and we'll get some predicted labels, or scored labels as they're called, and we can compare those to the original labels and see how well we're predicting. And that will allow me to evaluate the model as well and see those kind of performance metrics that we use for regression models, just to see how well it's performing. And then finally, I have an apply math operation, because what we predicted was the log of calories, and of course what I actually want is calories, so I want to convert that back to calories by using the exponential function. So I can go ahead and run that experiment. I've actually already run it. You can see the green ticks here. I've already run the experiment. So if I take a look at the score model, the output of that, and just see what we've got. Well, here are all the columns that are in my data set, including all the ones that I've generated. So there's my duration squared, effectively, duration to the power of 2, and the heart rate as well. And I've got my log of calories here. That's what I'm trying to predict. And then I've got the actual scored labels. That's what I did predict. You can see they're actually reasonably close. The distributions look pretty similar, and I can see the numbers themselves are fairly close. But that's not really surprising, because it's the log, so the differences are going to be fairly small. What I'm really interested in is the metrics that tell me how well that model is actually performing. So let's have a look at my evaluate model output. And we get a whole bunch of metrics here that we talked about briefly in the lecture. Now, the mean absolute error and root mean square error are they're absolute measures. So they're measuring, in this case, in the unit of log of calories. So it's kind of a meaningless number, this. It doesn't really help me very much. But the relative ones are quite useful. These are between 0 and 1. And for relative absolute error and relative squared error, I want them to be fairly close to 0. And it looks like, well, 0.02, 0.1 is maybe a little high, but they're close enough to 0 for me to be comfortable. And the coefficient of determination, or R squared we sometimes call it, we want that to be near 1, and it's 0.97. So actually that's looking pretty good. And if I look at my histogram, most of the error values are down towards the low end here. I haven't got any really big errors. I've got a few little outliers along the way, but most of my errors are quite small. So that tells me that it's predicting reasonably well. And then I've used this math operation here to convert my predicted log of calories back into calories. And if I just go and visualize that, I'll just move along to the end of here, and I can see here's the exponential of my scored label. So that's what is predicted in terms of calories. And if we just move that way slightly, here's the actual calories. So 172 versus 148, 99 versus 122, 178 versus 166, 55 versus 51. So they're kind of within the kind of ballpark. They're reasonably close to the predicted number of calories. Or the predicted value is reasonably close to the actual number of calories that were burned. So I can be reasonably confident that this model is producing a pretty good prediction for my calorie burn.